Hello, John Crooks here with part 5 in a series on pitch and pitch systems in tonal music. Today's presentation is an especially exciting one because we will be building a major scale using simple mathematics. Another way to refer to the major scale is as a diatonic set, and I'm going to be using that term quite a bit, so let's just unpack it. The diatonic set is the set of 7 pitches that can be formed into any one of the modes. So if you're familiar with how modes work in music, our most basic example is the major scale. C, D, E, F, G, A, B. That's 7 pitches that form a major scale. Also, those same pitches form the diatonic set. So today we will build a diatonic set using basic mathematics, and what we're going to be doing is called building a Pythagorean scale. So now we will build a major scale using some pretty basic mathematical processes. Let us first start by looking at these numbers right here. It is a stack of 3:2 ratios expressed as frequencies in hertz. And we're going to call this number right here 264 hertz, our fundamental pitch. Now, we discussed in an earlier presentation the idea of a tonic or most important pitch. So to build this scale, we're going to have 264 hertz be our tonic, and we will call it C. So let me enter in some numbers here, 264. And we're going to just multiply by 1.5 in order to create these 3:2 ratios. So we multiply by 1.5 to get 396. Multiply by another 1.5 to get 594. By 1.5 again to get 891. By 1.5 to get 1336.5. And by 1.5 once again to get 2004.8. So we now have a stack of 3:2 ratios, and we can see them here, forms, and we can hear them. There's our fundamental. Oh, and look, it's that 3:2 ratio. We have a perfect fifth. And so what we are building is a series of 3:2 ratios that sound like a series or a stack of fifths. Now this is our first step towards building this kind of a scale. However, if we play them in order, and we even have a name for these now, we can call them C, G, because C to G is a perfect fifth, G, D, because G to D is a perfect fifth, D, A, because D to A is a perfect fifth, A to E, and E to B. And if we play these in order, we hear something that does not sound like a scale. But this is our starting point for building a scale using this Pythagorean tuning system. So how do we actually turn this into something that sounds a little bit more like a scale? Well, it's very easy for us to see that these frequencies in hertz expand through much wider than a 2-to-1 octave range. Here, 264, our fundamental pitch, or C, 396 is fine, but already at 594, our D, we have gone beyond a 2-to-1 ratio octave. So what we need to do is turn our stack into a scale. And the way we do this is by dividing by powers of 2. So here we see our initial stack, the numbers 264, 396, 594, etc., etc. And so we just divide that 297D, sorry, that 594D, and make it 297. So let's change that. Divide the 891A and make it 445.5. Divide this 1336.5 E divided by 4, and you see we're collapsing the whole thing so that it fits within a 2-to-1 ratio octave. Finally, our 2004.8 we changed to 501.2. And now we have at least a series of pitches that are all within a 2-to-1 octave relationship. And let's hear what that sounds like. So this is great. We have actually built most of our major scale. C, D, E, G, A, B. We have almost a whole scale. And we can hear them now. Instead of sounding like a stack of fifths, it does sound like a cluster of pitches. Do, 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 da, da, da. So we've gone a long way now towards constructing a scale, but clearly we still have something that is missing, which is our pitch called F. So how are we going to get that one? Well, what we need to do is add another pitch to get our F. But if we keep on moving up in fifths from our B, we will get around to A only after we have all 12 of our pitches. So the way that we find our pitch called F is that we actually divide our fundamental pitch, or 264 C, by 1.5 instead of multiplying to get a 176 hertz F. And then we are able to multiply that to fit it within the range of 2-to-1. So let's just add that 176 hertz F right here. And let's take a moment and listen to our scale. That's a pretty cool thing. That's all the 7 pitches in our diatonic set sounding at once. And then if we want to hear this as a scale, notice we don't come around to the octave because we know that the octave will just be 264 times 2, or 528th. So we've done it. We've built a major scale using just basic mathematics. What we've done is we've taken a fundamental pitch called C at 264 hertz and multiplied by 1.5 to get D, E, G, A, and B. We've divided to fit all of these within an octave, and then we divided our fundamental pitch by 1.5 to get a 176 hertz F. We double that number to 352, and there we have our whole diatonic set. We can even write it out here as a nice circle of fifths. However, let's look a little bit more carefully at this circle of fifths. C to G, to D, to A, to E, to B. These are all great fifths. And then we go backwards to get F. And indeed, we do have a series of 7 fifths here, which is terrific. We're close to having a circular system of pitch. However, notice what happens here. F to B is not a perfect fifth. We hear B, F. That is a tritone. Da, 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 da. So although we're able to play a scale right now, we do not really have a circular system because that B to F does not circle around as a series of perfect fifths. So what we've done here is really pretty cool. We have built a major scale, or a diatonic set, using really basic mathematics. However, we don't have something that is truly circular. Moving forward to our next presentation, we will take what we just learned about this kind of tuning, which is again called Pythagorean tuning, and compare it to the triads that we had built in the previous presentation. So there, mission accomplished. We have figured out a way to derive a diatonic set, or a major scale, using just the simple mathematics of 3-to-2 ratios we have been talking about since almost the beginning of this series. It really is quite an accomplishment when we put it in historical context to think about the people who were developing music and musical instruments over the course of the past several hundreds and thousands of years. doing the study and experimentation necessary to create this very functional diatonic set. We were able to do it using the oscilloscope and basically a calculator to get the frequencies and hertz necessary to generate this diatonic set. Now what we will do is get a little bit more nuance into our understanding of tuning systems by comparing this Pythagorean set we just built to the triads we discussed in the previous two presentations. So stay tuned for the next episode.